Welcome to the Saturday session of the Rochester VHF Group. The VHF Group's online sessions are part of our educational and technical outreach program targeted to new licensees, VHF-bound technician licensees, future licensees, and seasoned veterans at all levels as we explore the invisible world around us through the magic of amateur radio. For more information about the Rochester VHF Group, please visit us on the web at rvhfg.org. There, you'll have access to a newsletter archive and a technical library for your reading enjoyment. Again, that's rvhfg.org. We also have an open email group on groups.io. Please consider joining RVHFG on groups.io as well. We've all referred to our bands in terms of wavelength. HFers even break down the 3.5 to 4.0 megahertz band in both and refer to it as both 80 meters and 75 meters. VHFers are well aware of the 6 meter and 2 meter bands. We've all seen printed graphs of how voltage changes along a wavelength, but few of us have ever set up a lab to visualize it for ourselves. A lecture line is a pair of parallel conductors that were historically used to measure the length of radio waves at HF and lower VHF frequencies. The last time they were mentioned in print, however, was in the mid-1900s. Seems so long ago, doesn't it? They form a short length of balanced transmission line. When attached to an RF source, standing waves form along their length. By sliding a conductive shorting bar along those lines, wavelength can be physically visualized using very simple components. Lecture lines are impractical, however, at microwave length frequencies, since such open wire feed line is replaced with coaxial cable and waveguide at these frequencies. Masterful microwaver Paul Wade, W1GHZ, will take us on a tour of how to similarly visualize microwave length RF, where such things are measured in centimeters and millimeters. Join us for this fascinating look and demonstration into a world that is otherwise invisible to the human eye. Today's session is titled Visualizing Microwaves. Our professor is Paul Wade, W1GHZ. A little bit about Paul. Paul was previously licensed as N1BWT and WA2ZZF. And he's been licensed since 1962 and has never made a contact below 50 megahertz. He's been a microwave experimenter for years and published numerous articles, as well as writing the microwave lengths column in QST magazine. He's active in the Vermont 10 gigahertz group and is past president of the Northeast Signal Group. An ongoing project is the W1GHZ Microwave Antenna Book, which can be found online at website w1ghz.org. In 1997, he was honored to be named by the Central States VHF Society as a recipient of the Chambers Award. He's been honored by the ARRL with the 2000 Microwave Development Award, and in 2001 with the Thomas Kirby Eastern VHF UHF Society Award, and in 2009 by Microwave Update and the North Texas Microwave Society with the Don Hilliard Award for technical contributions to the microwave community. We are truly honored to have him with us. Paul's a life member of the IEEE. After a long career in electrical engineering, including microwaves, computer hardware, and signal integrity, both he and Beth, N1SAI, are now happily retired in Vermont with a new puppy named Hannah. He's also a ski instructor for a time, so he enjoys skiing with his new bionic knee and skijoring with Hannah. That's a word you should Google if you don't know what it is. All I can tell you is Hannah's probably a bigger puppy than we know. Professor Wade, I turn today's Rochester VHF Group Saturday session over to you. Welcome aboard. Please go ahead and unmute your mic if you haven't already.
Thank you, Eb. Can you hear me? Wave if you can. Okay, good. All right, good to see all those faces from all over. Some of you got up real early or stayed up real late. So anyway, let's get going. Am I ready to share the screen, Ron? I think that's a thumbs up. Yes, so we'll do a few slides first just to get you going, and then we'll do the live demo or the total flop, whichever works. And as Ev said, if you have questions, type them in the chat window. I won't see them because I'd be too busy. But anyway, come on. All right, how do we get this to? There we go. So visualizing microwaves. Well, they're pretty much invisible to the eye, except really short ones in the 500 nanometer range, which we call light, but they're still electromagnetic radiation. So if you want to see radio waves or electromagnetic waves that have been traveling for a few thousand years, go outside tonight and look up. For the rest of them, we need an RF detector since our eyes don't do a very good job except at real high power, and that's not a really good idea. We can see them on a transmission line, in a waveguide, or even in space. So the microwaves are traveling at the speed of light. So not only are they invisible, they're going by real quick. And we know that wavelength is 300 million meters per second divided by the frequency. If you're really anal, it's 299 point a lot of decimal places. But well, the rest of us 300 is close enough. So at 1296, wavelength's 23 centimeters. Mention that because that's where we're going to do our demo. So if these lines are traveling down a transmission line and we put a short circuit at the end, the voltage has to be zero there all the time. So the wave effectively stands still with a standing wave on the line. And with a short circuit, we see not only zero there, but a zero every half wavelength. Whereas if we have a better load, then we just get a sine wave traveling down the line, and it's the same RMS amplitude anywhere if it's well matched. Okay, so what I've made up is a little coax line, an open coax that we can probe along. This, you can see, has a center conductor and 4 return conductors. We call them ground, but ground is a relative thing, especially at microwaves. Looking at the 4 outer conductors, you can see the evolution from a parallel open wire line to the coax, just adding a few more lines around it. So, okay. The other thing we need, let go away, yeah, is this sensitive RF detector. I found this little PC board from SV1AFN, who has some neat stuff for very good prices. And if you buy from him, you're helping a ham in a place where there aren't many jobs and not much economy. So, and you get good stuff too. This is an Analog Devices little detector chip, which I couldn't solder because those pads are probably 0.5 millimeter apart. And and the neat thing about this chip is that the output is 21 millivolts per dB, from minus 50 dBm to minus 3 dBm on my measurements. So it's at least those 50 dB of dynamic range. That's pretty damn good. And, if you calibrate it at anywhere in that range with something, you've got yourself a fairly accurate power meter from maybe 10 megahertz up to several gigahertz. There's a newer chip, 5517, that goes up to 10 gigs, which I'm playing with now, but we won't use that today. Okay, so there's the chip, there's the board. Come on, do something. And if we can get this to slide, and we need an RF probe to probe the line. So it's just a little stub of a center conductor on an SMA and a couple of standoffs just to keep it guided down the middle. And the whole assembly fits in a little specially made plastic container that for you older folks that floss your teeth probably recognize. Just happens to be the right size. Signal source is this little Chinese synthesizer here with push buttons to set the frequency. You can see it says 1296. Puts out a few milliwatts. And I put a low pass filter on because harmonics will also show up in the line and make the demonstration a little harder. So we're going to probe standing waves along the line here. And we've got a ruler so we can look at millimeters or centimeters. Centimeters what we're working in. Got a little LED bar graph attached to the detector, give relative output. And over here, this is a tone meter, which the frequency varies with the amplitude. So as you get more signal in, that's the DC signal from the detector, the frequency goes up. And we'll use those in a minute. So let's see. So again, we're going to probe on the transmission line with a sensitive detector, very low power level, maybe minus 30 dBm coming from the probe. That's a microwatt. So this is pretty safe. In the old days, you had to use light bulbs and watts of power to get it, get any indication. For indicators, we have the bar graph, the tone meter, and if I really cared about accurate dBm difference, I could use a digital voltmeter, measure the voltage, and calculate how many dB difference there is. So, okay. All right, time for a demo. Let's park this, boom, and get back to zooming. How do I get back on the screen? I always screw up here.
Probably the stop share button.
That one? No, that one. Share button, where's that? Stop share. Okay. Yes, thank you. Hello, Dan. Don. Okay. I guess if I'm the speaker, it picks random peoples to show me. So I'll have to fake this in a tiny little window then. Okay. So we come down here. There. I think you're looking at the line. Here's the LED display.
Paul, I'm going to interrupt here for just a moment, for the benefit of those who are online. There's a speaker view option in the upper right-hand corner of your screens if you have logged on through the Zoom application. If you choose that, then whatever Paul is broadcasting will take the majority of your screen so you can see what he's doing in greater detail. Sorry about that, Paul. Go right ahead.
Right. The only problem with speaker view is it doesn't show the speaker himself. Okay. How's that for volume? Okay, so that's the tone. So that's no signal there. I'm way out here as I come on the line. So as I slide down the line, get more signal, and a half wave away, we get a null, 0, up. Another half wave away, we get another 0. So we measured the distance between the two nulls, and we can calculate the wavelength and then the frequency. So that's with a short circuit on the end. Now I'm going to make an open circuit by taking the short off. Now, remember the 0 was roughly there. Now it's here and here. If you're paying attention, we've moved the nulls a quarter wave, but we haven't changed the distance between them. And now I'm going to put a 50 ohm load on. Now, this isn't exactly a 50 ohm line, but it's somewhere in the 60s range. So that's close enough there. So this will be fairly well matched, maybe a 1.5 VSWR. So very slight variation along the line, okay? So that's the first coax demonstration. Let's go back to the share screen and back to the PowerPoint, I think. Come on. Come on, thing. There it is.
So Paul, if I could ask a question.
Sure.
What would the significance be when you terminated it properly with the load? The fact that there was very little variation in voltage down that line, what does that imply?
Ready for the next slide. Okay, so standing wave ratio, or BISWAR, as hams call it. We probe the voltage along the line, and the difference between the ratio of the maximum to minimum is the VSWR, which we'd like to be 1, perfectly matched. And if the max and min are the same, it's 1, right? If it's not, we can calculate the actual ratio here. And okay, and I didn't do that part of the demo. All right, let's go back to that. Stop share. All righty. So come in from the side. Oops, lift it up a little. Bottom. So it's symmetrical all the way around. That's coax. The field is symmetrical all the way around. Let's back to share screen, back to, come on. All righty, there we go. So, all right. So with the short circuit, again, just to review, we did a high VSWR. When I measured it, the ratio of max to min was 27 dB, which is a VSWR of greater than 22, so that's pretty good. And a half wavelength, though you couldn't see the ruler well, was, again, we saw nulls at 17 and 5.5. Wherever I put the ruler down that time was 11.5 centimeters as a half wavelength. So that's 23 centimeters. Good. And back in the good old days, that's how you measured frequency, and sometimes you're even in the band. With an open circuit, The minimums are moved, but the wavelength still, half wavelength still 11.5 centimeters. Just we've reversed the minimum and maximum distances. And with the termination, low viswar, when I measured it was 3.3 dB, which is 1.5, and not perfect, but you know, these are the hobby tubing I had on hand. 100 ohms, it was 2.7, so it's not 100 ohms. And 68 ohms, it was a little better. But again, there's a connector on the end, there's some mismatches, so it's never going to be perfect, except by luck. Here's a 68 ohm termination. If anybody needs to make a real good termination, take a chip resistor and solder it on the end of a connector. It's good enough up to at least 1296, probably around 3 gigs before it starts to get bad. And if you want to make it even better, you could use 4 200 ohm resistors to make a nice 50 ohms, make them symmetrical, and that'll probably work to 10 gigs. Oh no. Enough PowerPoint, right? All right. Next demo. Okay, I'm gonna change. All right. First, I'm gonna change the frequency. Let's go back to demo mode. You shrink. You stop share. All right, and change the frequency. Now we're at 3456. And now, oh, let's go back to a short circuit. Not as clean, but let's see if I can get this working well. Oh, I know what's wrong. Somebody left the 1296 filter in line. That's why we're not getting any signal. Alrighty. There's another demo that a bandpass filter can remove harmonics. And sometimes you wonder why things don't work because you've forgotten some little detail like that. Of course, most of you have never made a dumb mistake, but I have. Okay, let's try it again. Now you notice the nulls are much closer together. Roughly 4.5 centimeters, since this 9 centimeter wavelength. All right, so what we'll do, I'll need a minute to switch to the waveguide, and so this would be a good time for questions. If I can stretch long enough to, I'll be right back.
Very good. So hang on, we do have some folks who have some questions that they would like to ask. So when you come back to the computer, we'll do that. We have a question from Phil, W1PJE. You've raised your hand. We have nothing in the chat room, so if you wouldn't mind, go ahead and unmute and ask your question.
Okay, Paul, this is fantastic. Have you tried putting a dielectric in your hobby tubing and seeing whether the velocity factor decreases? I just thought that that would be a nice complement to the demonstration.
Okay. Eb, are there any questions?
Oh,
Yeah, yes, we thought you were that you were unmuted and able to hear. So yes, there is a question. Phil, W1PJE is online, and he's going to field his question now. Go ahead, Phil.
Paul, hi. Yeah, greetings from Clinton, not far from you. Have you tried putting like Teflon in the open hobby brass tubing to see that the wavelength changed?
I haven't actually done that, but that would be a very good experiment. You could also immerse it in liquid and figure out the dielectric constant of the liquid.
I just think so many amateurs, want to know about velocity factors and coax, and right now they just look it up on a table, but you could actually demonstrate that. That would be fantastic.
That would be a good idea, yes.
Sure. So with that point, and thank you, Phil. I appreciate that. If you could go back to mute again. So Paul, based on that question, what does your gut tell you if there were a dielectric to be introduced? What effect would it have on your results?
It would shorten the wavelength because it slows the wave down.
And using this methodology, you could actually chart to see how much quantitatively.
Right, and you'd actually do it at the frequency of interest rather than at 1 megahertz where the manufacturers do it.
Very good, thank you.
So
continue on, that was our only question.
That was a very good one, thank you. All right, so let me just finish setting this up.
And while you're doing that, I'll remind the team, we are pretty close to capacity on this particular Saturday session, which is always a good thing. It is a good idea if you could please locate the chat function on your screens. No need to wait for a break. As you have questions or comments, please feel free to post them in the chat. I'll be happy to convey them on your behalf, and we can consider them as a group at that time. Paul, back to you.
Okay, let's go back to the sleep machine. Okay, so we're going to look at some waveguide because waveguide's a little more magical than coax. And I've made here a waveguide out of just some brass mesh screen. It's some sort of hobby product, and it's basically stretched to have holes in it. You could do it with window screen type stuff too. And I've left a slot here on the waveguide to probe through, but as you'll see, I can probe almost anywhere with this. So, and I've got a couple of surplus hunks at the ends just to hold it together. So let's see what the next slide is. Yes, so the waveguide is copper mesh.
So Paul, we're seeing your waveguide. We're not seeing your presentation.
Oh, you are? Huh.
You'll need to share your screen again.
Okay. Well, let's go back to here. I thought I pushed screen. Now I've lost it entirely. There we go. Share. Okay. All right. Now are we seeing it?
Yes, we are. Thank you.
Okay. So here's the waveguide. Let's try again. It's a copper mesh that we can probe through, and I've left a slot in the top. Just folded up some copper mesh into roughly the size of a waveguide. And I put a couple of surplus pieces at the ends to hold it all together, and so that I can connect a coax to it and get some signal into it. But basically, we've made a piece of waveguide that's got enough openings that we can probe it. So copper mesh waveguide, and it's slightly smaller than the commercial waveguide because stuffed in there. There's a slot in the center of the wide wall, And we can probe through the mesh using the same source and detector with a slightly longer probe to get into the coax. So here it is, the waveguide, signal coming in, and there's the detector. Okay. Okay, let's go back to live demo. Turn off, stop share. There we go. Okay. So LED. Too much signal. Somewhere here there was an attenuator. Well, there's another choice. We'll just turn the power down here. Okay. You notice that it doesn't change much as we go along here with the waveguide open at the end, because that's an antenna of sorts. That's why you don't look into the waveguide. We'll put a short circuit on there. I think a block of aluminum will do a fair job. Still too much signal. I wonder where I put that attenuator. I'd swear it was on that cable. It's probably on the floor with everything else. You know, if you ever need parts to build a transverter or something, just come sweep up my floor. All righty. Anyway, we'll fake it. Okay. Let's see. I know. We'll go back to the shorter detector. That'll work too. No, it won't. Will it? Maybe. Shorter probe, rather. All right. Well, I'll have to take my word for it that the wavelength is longer in the waveguide than in the coax. Oh. Give me 1 second to grab an attenuator. We'll do this right.
And while we're waiting for Paul to find his attenuator, I just wanted to remind folks, this is a presentation that Paul did at the VHF Super Conference in Washington, D.C. Just last year. Sadly, we won't be seeing another one of those conferences for a little while, but we certainly look forward to them when they can resume. They're a world of great information, and you get to see these types of things live and in person at them.
Actually, you're probably seeing it better today than 100 feet back in an auditorium, but
True, true.
All righty. Here we go. Knock everything down 20 dB. That should help. Okay.
Paul, while you're getting set up there, there's a question about the gap in your waveguide. Is there any significance to that, or is it just a vestige of having put something together with
I will
hardware?
get to that.
Very good.
Yes, we will. As soon as I get to where I can probe this effectively, we can do that part of the demo. Okay, now let's try. Come on. Okay, there's a minimum. And there's another minimum, and they're closer to 10 centimeters apart than the 4.5 we had in coax. Okay. And as I said, when we're matched, it's much less variation, or not matched, but when we leave it open as yep. And if you're careful, you can move this short around and get the reflected power there. Now, there's a signal here, but if I rotate it 90 degrees, there's almost none. All right, so it's
Paul, is the
polarized.
LED indicator available to us?
Pardon?
Is the LED indicator, the visual indicator, something that you can put in the field of the camera?
Yeah. Oh, is it? Can you not see it?
It's kind of washed out.
Oh, okay. This thing's. Sorry about that. Yeah. Yeah. Live demos are always tricky. Can you see it now?
Oh, much better. Thank you.
Okay. So. Okay. And as I probe in the waveguide, there we go. Oh, yeah. Oh, yeah. And let's do the short circuit again. All right. Well, not great. And as I probe off to the side here, as I probe along the guy in the transverse direction, you'd find the field drops off as we get to the edge. So, and the polarization. Okay, so back to talking. You hush up. Where are we going? Yeah. Okay, so didn't get a real good demo of this, but we get a very high viswar. And the wavelength in the guide, as I said, is closer to, or the minimum, or closer to 10 centimeters apart than to 4.5 we saw it in waveguide. So in the guide, it's a 17 centimeter wavelength, and in free space, it's 8.7 centimeters. So the wavelength in guide is longer than the wavelength in space. And what's that mean? Well, your first thought should be, that's going faster than the speed of light. Which brings us to phase velocity in waveguide, which I can't explain in an hour, but it is one of the magic things about waveguide. So with the open, we have low viswar because it's radiating as an antenna and it's polarized, as I showed you. So There we go. And with the waveguide properly terminated, we should have a low vis wire, but we'll skip that demo. So if we probe across the waveguide, looking in the end here, we would see that the electric field falls off to the edge. Obviously, it has to be 0 here because the sidewall shorts it out. The thing about the hole in the center is that although the field is high there, it's symmetrical around there. So if we cut the guide there, there's no voltage difference between one side and the other, so that we can make a slot there with no effect. If we were to make a slot here, we'd be making a slot antenna because there would be a difference between the two sides. That's how we make waveguide slot antennas. And I won't do it today, but I did it in a smaller waveguide, which makes the waveguide, the wavelength in waveguide is proportional to how close you are to the cutoff frequency where the guide is. Guide has to be at least half a wavelength wide or nothing goes through. And the closer you get to that wavelength, the longer the wavelength, guide wavelength gets. And I did that, but that was kind of messy, so we won't do that today. So, summary, if we have an open or a mesh structure, and certainly we can make it coax with the mesh stuff, and a sensitive detector, we can look at electric fields and coax, waveguide, antennas. We can look for leakage in your microwave oven or your cabinet around your rig. You know, if you're running high power, you might want to look for leakage running around your shack. Let's do the antenna demo anyway. Stop share. Okay, so. So you can see the radiation is strongest in the center and it falls off to the sides. It's a very wide antenna, but you can actually get a rough idea of a radiation pattern playing with this. All right, so where are we back to? Sharing screen, yes. All right, and the other things you could play with are optical things like reflections. Yeah, well, I wonder if we could do that. I bet we could do that one. You can play with the reflection there. You could do refraction with the dielectrics. Good diffraction, that's a good one. That takes a little fiddling to get right. And polarization we demonstrated, but you can check that. You know, if you have an antenna that you think is circularly polarized, you could at least poke around and see that it sort of is. So once you've got a detector like this, you can do a lot of things. Or it's just a cheap power meter. There we go. So let's see, out of screen sharing, I guess you'll have to look at me again. All righty, so. And Phil says a bottle of motor oil makes a great demonstration of dielectric for in the coax. The reason I didn't do it is it's a bitch to clean it up again.
That's true. We also have a question here from Ron. If a probe was a loop instead of a linear probe that you're using, would it be sensitive to the magnetic field?
The answer is yes. Problem is making a loop small enough to be a loop and not a probe as well at microwave frequencies is difficult. The ones I've seen, you take a piece of semi-rigid coax and take a very little bit of the center out the end and bend it back on itself and hope it's small enough. But
Very good.
at lower frequencies, that does work. So maybe make a big waveguide and get yourself a piece of duct and do it at 2 meters.
Paul, you made a comment earlier that engendered a question as well. You had mentioned that had the slot in the waveguide not been in the center of the wide area, that it would actually radiate. And
Yes.
you had mentioned something about slot antennas.
Right.
Could you amplify that thought a little bit more and explore that with us verbally?
Okay. I don't have a picture on this computer, but if you look in my antenna book, there's a whole chapter on it. But basically, if you make a slot off center, it will tend to radiate. If you make it a half wavelength long, where it's resonate, it'll radiate a lot better. And if you put a series of them spaced half wavelength apart, then you made an array of them and can actually get some gain out of them.
So as we look at slot antennas, there are pictures of them all over the place.
Yes.
Even on eBay, there are people who are selling slot antennas for 24 gigahertz. If you take a look at them, the waveguide is there, and the slots appear to be on either side of the center line and then spaced appropriately. Is that what you refer to as having radiating elements?
That is, yes.
Provide the gain that you're looking for.
A vertical slot is equivalent to a horizontal dipole through the magic of complementary subject. So I had another thought there, but it went away. Okay, was there another question? Well, maybe it'll come back.
Round waveguide.
Oh,
any,
yes,
any
round
differences? Yeah.
Okay, the difference is that in round waveguide, the polarization is not defined. So if you can, whatever polarization you put in is what you get out, unless there's some discontinuity that makes it rotate, which people who've tried to use water pipe, for instance, at 10 gigahertz as transmission line, as waveguide, sometimes find that they have to rotate the probe at one end to get it right at the other end.
And how about elliptical waveguide? That's kind of halfway in between the two. Any special considerations there?
Yeah, it's getting from some other kind of waveguide in and out of it. But yes, elliptical waveguide is popular for, or I won't say popular, but is used for commercial applications because you can bend it and still maintain its characteristic if you make a large bend, of course. Regular waveguide is hard to bend. And so you end up using mitered elbows usually, which come in maybe 45 and 90 degrees, but odd angles are really hard. And or bending, yeah.
Oh, sure. Bending a waveguide isn't the most easy thing to do, for sure. Doing it right without crunching it, for sure.
Right. So.
Well, good, Paul. Thank you. I'm going to continue to see if there are any further questions. Anything else for us to cover today, or did you do what you needed to do?
No, I think what I'm trying to show you is that with very simple equipment and low power, so it's safe, you can play around, learn for yourself, and see things for yourself that you can only read about in the books. And it's a very useful little piece of test equipment, having a sensitive probe.
Very good. Well, Paul, I sure thank you. We've had a really good good volume of folks who joined our session today. So with that, I'd like to conclude this Saturday session of the Rochester VHF Group. I would like to publicly thank Paul Wade, W1GHZ, for bringing us such an interesting lab. It really drove home the issues of wavelength, standing waves, VSWR, all concepts that we read about, but rarely have the opportunity to visualize as we did today. Hopefully we're going to leave today with a little greater understanding of what actually goes on and what we read about. At this time, as I promised early on, I'd like to invite attendees to unmute.
One more point, Ev.
Oh, sorry.
Okay. Now, probably a few of you will have questions that occur to you in the future. Just send me email. No problem.
Oh, outstanding. Thank you. Thank you.